The Chernobyl Nuclear Power Plant, located near the city of Pripyat in Soviet Ukraine, was a symbol of progress and technological prowess. It stood as a testament to the Soviet Union's ambition to harness nuclear energy for peaceful purposes, showcasing their ability to build and operate one of the most advanced nuclear facilities of its time. Constructed in the 1970s, the plant was intended to be a shining example of Soviet engineering, supplying electricity to a vast area. The construction process was a massive undertaking involving thousands of workers and engineers who toiled day and night to bring the ambitious project to life. The plant's completion was celebrated as a major achievement, marking a new era of energy production in the Soviet Union. The plant housed 4 RBMK-1000 reactors, known for their powerful energy output. These reactors were designed to produce not only electricity, but also plutonium for the Soviet nuclear weapons program. The RBMK reactors were unique in their design, utilizing graphite moderators and water coolant, which allowed for high efficiency and output. These reactors, however, possessed inherent design flaws that would later prove catastrophic. The RBMK design had a positive void coefficient, meaning that an increase in steam production could lead to a rapid increase in reactor power. This characteristic made the reactors inherently unstable under certain conditions, a fact that was known to some engineers but not widely acknowledged. The city of Pripyat, built to house the plant's workers and their families, was a model Soviet city, boasting modern amenities and a vibrant community. It featured schools, hospitals, cultural centers, and recreational facilities, all designed to provide a high quality of life for its residents. The city was a showcase of Soviet urban planning intended to attract skilled workers to the region. Life in Pripyat revolved around the power plant, with many residents employed directly or indirectly by the facility. The plant was the economic heart of the city, providing jobs and stability. Daily life in Pripyat was closely tied to the rhythms of the plant's operations, with shifts and schedules dictating the flow of the community. The city, however, was built on a foundation of secrecy, with information about the plant's operations tightly controlled. The Soviet government maintained strict oversight of the plant, and any issues or concerns were often classified and kept from the public eye. This culture of secrecy extended to the residents of Pripyat, who were largely unaware of the potential dangers posed by the plant. As the plant ramped up operations, safety concerns were raised, but often dismissed or downplayed. Engineers and workers who voiced their worries were frequently ignored or silenced, as the priority was to maintain high production levels. The plant's management was under constant pressure to meet ambitious targets, leading to a disregard for safety protocols. There were reports of minor accidents and near misses, but these were kept hidden from the public. Whistleblowers and concerned engineers who tried to bring attention to these issues faced significant pushback and were often labeled as troublemakers. The culture of secrecy and denial created an environment where small problems could escalate into major disasters. The pressure to meet production quotas often took precedence over safety protocols, creating a culture of complacency and risk-taking. Workers were pushed to their limits, and the intense work environment fostered a sense of urgency that overshadowed caution. This relentless drive for productivity, combined with the inherent flaws in the reactor design, set the stage for the catastrophic events that would unfold in April 1986. At the heart of the Chernobyl disaster lay a combination of design flaws in the RBMK-1000 reactor, a type of reactor that was unique to the Soviet Union. This reactor was designed not only for electricity generation but also for plutonium production, which added layers of complexity and risk. The Soviet nuclear industry at the time was plagued by systemic issues that exacerbated these design flaws. The industry was characterized by a culture of secrecy and a lack of transparency, which meant that problems were often hidden rather than addressed. The RBMK-1000 reactor's design was inherently flawed. Unlike Western reactors, which typically included robust containment structures to prevent the release of radioactive material, the RBMK-1000 lacked this crucial safety feature. This omission meant that in the event of an accident, there was nothing to stop radioactive material from being released directly into the atmosphere. The absence of a containment structure was a significant oversight. In Western reactors, the containment structure serves as a final barrier, designed to contain any radioactive material that might be released during an accident. Without this, the RBMK-1000 was vulnerable to catastrophic releases of radiation. When the Chernobyl disaster occurred, the lack of a containment structure meant that radioactive material was released directly into the atmosphere, leading to widespread contamination and long-term environmental damage. The immediate aftermath saw explosions and fires that further exacerbated the release of radioactive substances. Another critical design flaw was the reactor's susceptibility to a phenomenon known as a positive void coefficient. This occurs when a power surge leads to an increase in steam production, which in turn accelerates the nuclear reaction. In the RBMK-1000, this could result in an uncontrolled chain reaction, making the reactor extremely dangerous under certain conditions. Beyond the technical flaws, the Soviet nuclear industry was hampered by systemic issues. A culture of secrecy pervaded the industry, with information about safety issues often suppressed. This lack of transparency meant that problems were not openly discussed or addressed, creating an environment where accidents were more likely to occur. Safety reports were frequently suppressed, and there was a reluctance to acknowledge problems or seek assistance from the international community. This insular approach prevented the sharing of knowledge and best practices that could have improved safety standards. The culture of secrecy was compounded by inadequate training and safety protocols. Workers at the Chernobyl plant and across the Soviet nuclear industry often lacked the necessary training to handle emergencies effectively. Safety protocols were either insufficient or not properly enforced, creating a fertile ground for disaster. In the wake of the Chernobyl disaster, the international community recognized the need for greater transparency and cooperation in the nuclear industry. Modern nuclear safety measures now emphasize robust containment structures, comprehensive training programs, and open communication about safety issues. The lessons learned from Chernobyl have led to significant improvements in nuclear safety standards worldwide. Today, the Chernobyl exclusion zone stands as a stark reminder of the consequences of design flaws and systemic issues in the nuclear industry. While nature has begun to reclaim the area, the long-term effects of the disaster continue to be felt. The Chernobyl Memorial serves as a poignant reminder of the need for vigilance and continuous improvement in nuclear safety. As we look to the future, the lessons of Chernobyl underscore the importance of rigorous safety standards, transparent communication, and international collaboration in the nuclear industry. By learning from past mistakes, we can work towards a safer and more secure future for nuclear power. On the fateful night of April 26, 1986, the world witnessed one of the most catastrophic nuclear disasters in history. A routine safety test was scheduled at Chernobyl's reactor number 4, a test that was supposed to be straightforward and uneventful. The purpose of this test was to simulate a power failure and assess the reactor's ability to cool itself using backup generators. This was a critical procedure to ensure the reactor's safety in the event of an actual power outage. However, what was meant to be a simple test quickly spiraled out of control. A series of miscommunications, violations of safety procedures, and inherent design flaws in the reactor conspired to create the perfect storm. The test began with a gradual reduction in reactor power, a standard procedure. But due to communication errors and a lack of awareness of the reactor's instability, the power level dropped far lower than intended, setting the stage for disaster. This significant drop in power created conditions for the positive void coefficient to take effect, a dangerous phenomenon that made the reactor highly unstable. The operators, unaware of the full extent of the reactor's instability, continued with the test. As the operators attempted to regain control of the situation, they encountered a fatal flaw in the reactor's control rods. These rods, which were supposed to slow down the nuclear reaction, had a critical design flaw. The control rods were tipped with graphite, a material that initially accelerated the nuclear reaction instead of slowing it down. This design flaw was catastrophic, especially given the reactor's already unstable state. The combination of the reactor's instability and the flawed control rods led to a rapid and uncontrollable power surge. Within moments, the reactor's power output skyrocketed, leading to a massive explosion that blew the roof off the reactor building. The explosion released a significant amount of radioactive material into the atmosphere, creating an immediate and severe health hazard. Firefighters and emergency response teams were quickly dispatched to the scene, but many were unaware of the true extent of the danger they faced. In the nearby town of Pripyat, residents were initially told that the situation was under control. It wasn't until hours later that an evacuation order was issued, and by then, many had already been exposed to dangerous levels of radiation. The aftermath of the disaster was devastating. The area around the reactor, now known as the Chernobyl exclusion zone, remains uninhabitable to this day. The once thriving town of Pripyat stands as a ghost town, a haunting reminder of the catastrophe. The Chernobyl disaster had far-reaching consequences, prompting a re-evaluation of nuclear safety protocols worldwide. Scientists and engineers from around the globe have studied the incident extensively, leading to significant improvements in reactor design and emergency response procedures. Today, memorials and commemorative events honor the victims of the Chernobyl disaster. The lessons learned from this tragic event continue to shape the future of nuclear energy, reminding us of the importance of safety and vigilance in the face of potential catastrophe. The power surge in Reactor 4 triggered a chain reaction that quickly spiraled out of control. The reactor's power output surged to over 10 times its normal operating level, causing a massive increase in temperature and pressure within the reactor core. The intense heat caused the fuel rods to rupture, releasing radioactive fission products into the reactor's cooling water. The superheated cooling water flashed into steam, causing a steam explosion that ripped apart the reactor vessel and destroyed the reactor building's roof. The explosion released a massive plume of radioactive material into the atmosphere, carrying radioactive isotopes of iodine, cesium, strontium, and other dangerous elements. The explosion and subsequent fire at the reactor core raged for days, releasing vast quantities of radioactive material into the environment. The plume of radioactive material drifted over large parts of the Soviet Union and Europe, contaminating soil, water, and vegetation. The Chernobyl disaster was the world's worst nuclear accident, releasing far more radiation than the atomic bombings of Hiroshima and Nagasaki combined.